I like this idea that we're actually really literally the universe's mechanism of expressing creativity and making things possible that would not be possible.
What is life? It's perhaps the biggest unanswered question in all of science. And what's the connection between the origin of life on Earth and the search for alien life forms in the cosmos?
Well, I think we won't know anything about whether aliens are likely or not unless we know the mechanism for the origin of life.
Could a revolutionary new theory hold the key to detecting life beyond Earth? And is consciousness an inevitable outcome of life's complexity? Or is it something much more mysterious?
I kind of think of the state of life and consciousness like trying to talk about gravity before the generation of Newton and Galileo.
Professor Sara Walker, an incredible astrobiologist and theoretical physicist, joins me for her second appearance on the podcast today to illuminate these fascinating questions and more on the occasion of the release of her fantastic new book, Life as No One Knows It: The Physics of Life's Emergence. Sara's groundbreaking research dives deep into the origin of life, exploring how the same principles that govern life on Earth might apply to life elsewhere in the universe.
That's deeply intrinsic to what life is that life is actually the history wrapped up in the present.
Can we make life? Can we produce it here in the lab? Sara thinks we might just be able to, and that would be a key unlock to our understanding of mankind's oldest question. With her pioneering work on assembly theory done with her close collaborator and past guest Lee Cronin, she's redefining how we search for alien life by focusing on the complexity of the molecules that matter most. This conversation will change how you see the universe and life itself. Let's go. Why do you turn almost immediately and pivot from origin of life to looking for aliens elsewhere in the universe? What's the relationship?
Well, I think we won't know anything about whether aliens are likely or not unless we know the mechanism for the origin of life. So I think you actually can't decouple those problems. And the fact that we normally think about them as being separate is not really the right framing. So if you think about, in part, it's actually like my cosmology background that motivates me to kind of connect alien life to origins of life. Because, if you think about the connection between particle physics and cosmology and how much we understand about sort of universal principles and, what happens elsewhere in the universe because we do particle physics experiments on Earth, my thinking is that if we understand the origin of life and we can build an experimental paradigm here to try to look for aliens in the lab by doing new origin of life experiments, then we understand more about the mechanisms of how that happens on other planets, and we might be able to think more universally about life. So that's sort of the connection that I'm trying to draw and using that background.
I can't really tell if you're an alien, optimist or pessimist. Do you feel like, that there's guaranteed, I always hear this, it's the universe is so big and, it's got to be life out there. Even my past guest, Ann Drurian, said, in Contact, that if there's no life out there, it's an awful waste of space. But, the universe, Mother Nature, God, whatever you like, is under no obligation to make sense to us. So are you an alien maximist? And furthermore, if there are aliens, are they intelligent and communicative, if you can answer those?
This is a question I probably change my mind on pretty regularly, actually. And it might be the one place that I'm not as optimistic as everyone else. So usually I'm way more optimistic than most people, but this is because I think about this question and I try to think about it in the most rigorous way as a scientist. I really try not to have a strong opinion on it outside of observational evidence. And we don't have evidence supporting that life is common or that it's rare. So I don't really want to build a strong prior in my mind about whether I think it's out there or not until we understand what we're looking for and how to look for it. So, that's sort of the scientist part of my brain. And then the sort of, how do I feel about the problem actually oscillates between thinking it's incredibly common and it's incredibly rare. Right now, I'm kind of on the, I'm not sure any other life is out there kind of side of the spectrum, but I don't know how long I'm going to sit with that. And as far as whether other life is intelligent or not, I think that's a hard question. I don't see any reason so a lot of the way I think about life is more at the planetary scale than people usually do. So people usually think about like microbes or they think about radio communicating civilizations. And I'm much more interested in universal properties of life and understanding sort of deep regularities and like fundamental physics of life. And so for me, thinking about life as the process that builds complexity in the universe feels the most natural way of talking about it. And I don't see any reason that if that process starts happening on a planet, it would cap out at something that was less intelligent than us. So in general, I think if there is other life out there at some point in its evolution, it should become something that we might quote unquote call intelligent. The nature of that intelligence might be very different than what's evolved on Earth, though. And those are obviously the most interesting questions to ask.
I always joke, next to the origin of the universe, that's the most interesting thing you can study.
Yeah. You picked the most interesting one, right?
I'm a little biased, but
Yeah.
you left the most interesting to go into that second. But anyway, they're both fascinating. I want to do now what you're never supposed to do, which is to judge a book by its cover. And the world has been waiting for this book for half a decade now, since we met on Clubhouse 4 or 5 years ago now. Life as we know it, the physics of life's emergence, and then explain the beautiful cover art. But first, before you do that, explain the meaning of this word I'm Ari, or if you get rid of the R, it's I'm AI. So I've always wondered what's the origin of your middle name?
Yeah, it's a bit of a funny story. So my mom gave me my name, and she's an antique dealer. So she really likes old stuff. And she has these sets of dishes. They're called Amari dishes. So that name, which were imported from Japan in the 1800s. And it's actually very funny because she named me Amari because she thought that the name meant flower, because that's sort of the pattern on these dishes. And it wasn't until I was... Oh gosh, I think I must have been a postdoc. I was going to visit Japan, and I had a colleague, who knew a lot about Japanese culture and things that I was interacting with there, and he pointed out to me that Amari is actually not the name for flour. It's actually the name of a port in Japan, and it turns out to be the port the dishes were exported to America from. So I'm actually technically named after a city in Japan. But I think also the other thing this colleague pointed out to me is that I think my first name means dish. So I'm sort of like my name in Japanese is like related to dish plate or something. I don't know. But anyway, that's the origin of my name. It comes from my mom and her interest in old things and liking something that wasn't the usual name.
Okay, and now we know the origin of your middle name. We can move on.
So it has nothing to do with family history or anything. It's just totally a very odd family story.
I would have loved it if it was I'm AI and your mother presupposed that. But now into the impossible, judging the book by its cover. So tell us the title, the subtitle, and the cover art.
So the title of the book is Life as No One Knows It, The Physics of Life's Emergence. And actually, that was a title that I came up with together with my editor. And so she iterated with me quite a lot. But in part, it was quite funny because my original title for the book, when I pitched it, was The Hard Problem of Life. And that was a play on the hard problem of consciousness. And I remember having this conversation with my editor, and she's like, I think calling it a hard problem is going to be a little bit hard for the reader. So this is where the fact that I was talking about, not just life as we don't know it, but like this idea of discovering totally new ideas that we could, play with that and think about it as life as no one yet knows it. So that's sort of the origin of the title of the book. And then the cover art was really because the book is, I think, it's very optimistic because that's my personality, and kind of has like a bright outlook on the nature of these problems and like an excitement about thinking about fundamental problems. But it's also like, a popular science book. So there was kind of a discussion about how do we make it look academic, but also exciting. So that's kind of the cover art. And I was very happy with the style that they came up with. It's pretty cool.
Yeah, it's very evocative.
It's such a fun process, and you don't even know, like, until you go writing a book, like all these like little decisions you have to make and all these things. So like, but I was kind of surprised going into it.
I was surprised how much the cover makes a difference. And it turns out if you have a book, a rare book, say, Charles Darwin, Origin of Species, and it's missing like the dust jacket, then it loses 90% of its value. And I always thought, like, what's the deal with dust jacket? I mean, they always fall off. They're kind of annoying.
Yeah, that's the other thing I was going to say that I really like about the book, though, is like they have pink lettering on and I didn't pick that on the binding, but I was like, oh my God, I love that. It's like pink metallic.
It's really nice looking. It's and it's well bound, and I listened to the audiobook too. Penguin Random House was kind enough to send it to me, and the Kindle book, and everyone should get all three versions, I always say.
Yeah, and I narrated the audiobook, which was quite an experience. It was the first time I've ever done that, and it took like 3 days. And it was very funny because I was in Santa Fe at the time. So I was like talking about all these stories about being at Santa Fe or like working with my colleagues there. And I'm like, but I'm there now. So it was like a lived experience. It was funny.
The book is beautifully done and presented. The audiobook is great. It matches some of the long Clubhouse sessions we had together in length. So I want to talk about another kind of, slightly controversial topic, or controversy, as they might say over in the UK. And that's, the relationship of consciousness and life. And you speak a lot about that in the book. And it's, I've had on people like David Chalmers and Sam Harris and Daniel Dennett and stuff. And we talk about the hard problem of consciousness. You talk about that. You open up the book talking about that early on. And when I had David Chalmers on, I asked him, if he's from Australia, right? So I asked him if I had on, AC/DC, and I don't ask them to play You Shook Me All Night Long, I'm a terrible podcast host. So first I have to ask you about assembly theory. And then we're going to talk about what is the possible relationship of assembly theory with its highly computative and notions of complexity and even into entropy and thermodynamics. What is the relationship between that, consciousness, and life? Are they kind of necessary and sufficient, or what's the relationship between consciousness and assembly theory and life?
Assembly theory is born out of an interest in solving the origin of life question. And so with the origin of life, you're presented with the issue that you need to be able to differentiate when the transition from non-living to living matter happens. So you have to have in some sense, what my colleague Paul Davies, who I know has been on the show too, calls a life meter. You need some measure of like, this was not alive and this is alive. And it turns out that's very non-trivial to do, obviously, because in some sense, what you're doing is formalizing a notion of what life is and making it experimentally testable. And so the way that we've actually managed to do that, and why I'm so excited about assembly theory is a conjecture that life is the only mechanism the universe has for generating complex objects. And the key conjecture there is, if you think about chemical space is like the space of all possible molecular configurations. And you can have like very simple molecules like methane, which is just a carbon attached to, several hydrogen. But then you might have more complex molecules like DNA. And there's some boundary from the simple to the complex that you actually need to have information or selection or evolution to cross. And assembly theory has a way of formalizing that. We talk about it in terms of the assembly index and the copy number of the object. The assembly index is the minimal number of steps. If you take parts like the bonds that make up a molecule, or it's easier for people often to think about Lego building blocks. If you take the blocks and you stick them together and then you take parts and you build them again, any parts that you've used you can reuse, and you look at the minimal structure of a path to get to a complex object. So it might be like a molecule of DNA in chemistry, and it might be like Hogwarts Castle in Lego. And so if you see such a complex object in high abundance, it's suggestive that there had to be an evolutionary mechanism to create it. And so assembly theory makes a conjecture that there's a formal boundary or that there's actually a physical boundary. There's a complexity threshold only life can cross. And we can measure assembly index in the lab with standard laboratory equipment like mass spec. And so my colleague Lee Cronin, who originated the ideas of assembly theory, actually derived it as a measure because he wants to do original life experiments in the lab and be able to verify it experimentally. And so his lab went in and took non-living and living samples, things like Murchison meteorite, which is a really complex inorganic sample from the early solar system, whiskey, and they basically were able to classify, in a sort of with mass spectrometry, the complexity, or the assembly is actually the more formal way of saying it, the assembly of these different kind of molecular systems, and show that living things were the only things that generated really high assembly molecules. So that's sort of our starting point, is to say that the origin of life is basically the process of crossing this threshold. And that's really the question we were most interested in. But assembly theory offers some new framings of some really interesting questions. And it's super funny with writing the book because I started it before I really got very into assembly theory. I was like already, thinking about information and causation in life and the fact that they were supposed to be fundamental, to what life is. So I had written this paper with Paul more than a decade ago about the origin of life transition maybe being quantifiable in terms of information and causation. But I didn't really think about I wasn't really optimistic that we were going to be able to test these kind of ideas, or there was like a really formal mechanism for developing a theory, until I started working with Lee on assembly theory. And so I was already writing this book about these ideas about information and causation and a transition at the origin of life and new fundamental physics needed. And at the same time, I was like developing this theory with Lee. So a lot of it ended up in the book, which is kind of exciting. But the reason I'm so excited about it is it's a way that we can go in the lab and measure a feature that we might associate with what we call life, and allow us to test hypotheses about the mechanisms for the origin of life, and also to look for alien examples on other planets. Because now if we're saying we're not looking for DNA, or we're not looking for amino acids that, happen to be used in proteins on Earth, we're actually going out and looking for complexity in the universe. To me, that seems a much more agnostic and tractable way of searching for life. This doesn't get to like the deep questions of the nature of consciousness and stuff like that yet, but I wanted to give kind of like the background of like the pragmatic approach. And yeah, so we can get into some of that, unless there's like a specific thing you want to ask about what I've said so far.
I just, can you you talk about life, there are examples of burgeoning life, potential life. My favorite example are oil droplets, and of course there's inevitably the notion of panpsychism, which I find almost virulently toxic to the soul, but that might be my predilection. At what level is consciousness a requirement, or maybe I'm totally wrong, and maybe life is a prerequisite for consciousness. Although if you believe in panpsychism, that's not the case, right?
I think the aversion I'm feeling from you is just the physicist's normal aversion to like, if I can't measure it and you say it's a property of everything, like it's not really helpful in some sense, or at least that's sort of sometimes how I feel about different panpsychist arguments. Like, it's an interesting idea, but what's the testable hypothesis there, and how do I measure it? And the issue with the problems of life and consciousness has just traditionally been that we have very subjective and colloquial ideas about what these phenomena are. But the reason that they're so hard is we haven't regularized a concept of consciousness or life that we feel like that really, captures what we do in the scientific method to validate theories, right? So for me, I kind of think of the state of life and consciousness, like trying to talk about gravity before the generation of Newton and Galileo. Like, you could talk about things falling, and you could make observations about, certain planets and, wandering stars, you would call them. You wouldn't even know they were planets, right, in the night sky. But you would have no formal way of making a connection that they had the same mechanism, and you would have no concept of something that we later came to understand as the theory of gravitation. So we knew gravity existed long before we had a theory or a way of measuring its existence or understanding what it was. And I think life and consciousness, we have ample evidence that they're real features of our reality, but we don't know how to talk about them. And so what we have seen in the history of physics repeatedly is that when we find new ways of measuring things and new ways of testing ideas, we come up with theories that seem very counterintuitive in what they say about what those phenomena are. Gravity, originally, maybe people would think that, like the color of an object mattered to its attraction to the planet, or actually, there's always the famous experiments about like trying to test whether friction mattered or not with feathers and balls and these kind of things, right? So people didn't really know what the relevant properties were. They had to identify mass was a relevant property. And, over many centuries, that led to us realizing things like, once you assume, like you have clocks and you can measure the constancy of the speed of light, then you get to things like the curvature of space-time is necessary to explain the fact that we're sitting in our chairs. So very counterintuitive things come out of the fact that we reason from measurements we can make. In the case of life, I think this is why I'm excited about assembly theory, is because it is something we can go in the lab and measure. We really think this is a property of molecules. It's not that you can just measure it with a mass spec. Lee's lab has an amazing paper where they show that they can measure it in infrared and NMR spectroscopy, and they get consistent values for the same molecule across different measurement modalities. So this idea that the causation or complexity built into a molecule is actually a physical feature of the molecule is now a measurable attribute. And if you can validate in an experiment that life is the only thing that generates high complexity, that gives you a starting point for scaffolding into a theory that would explain the regularities that we associate with life. And so that's sort of where we're at. And the regularities I'm most interested in there that relate to your question of consciousness and what I discuss in the book is this idea that life is sort of the universe's way of exploring the space of possibilities that could exist when that space gets too large. And it does it by building these objects stepwise and making them deeper and deeper in time. So this idea of this assembly index as like a measure of how much causation or time went into building an object or how much information actually becomes a feature of the object. So evolved objects are now things that don't just have a physical size, like you can measure the 3 dimensions, but they actually have a size and time. And this is the sort of very radical departure that and like philosophical leap that I've made with assembly theory that, is the biggest departure from standard physics. But the reason I'm excited about it is it reconciles a lot of issues with why fundamental physics and also our current theories of physics have been inadequate to solve the origin of life or explain life that I had covered with Paul in that early paper long before assembly theory. We pointed out a whole bunch of hallmark features that we couldn't really reconcile, and I think assembly theory will solve all of them. Where it gets interesting for consciousness is as evolutionary structures become deeper and deeper in time, they're bigger in this they're getting larger and larger in this very high dimensional space, the assembly space, which is about this. You can almost think of it as a space of functions if you want to do a computational analogy. But assembly theory is very different than computational complexity theory or what has come out of computer science as far as like theoretical computer science for theories about the nature of computation. It says some very different things, but it has some similarities in terms of what it says about the structure of reality that people might think sound more like a theory from how people think about the universe as a computation than they do as a theory of physics. But it's a physics theory. So it's in this interesting intersection. But as far as the problem of consciousness, what I think assembly theory can say about it is that as structures become evolutionary more deep, they have more of their physical structure in this sort of temporal structure, this sort of like rolled up amount of causation in the present object than they have in the spatial structure. And things that have that are very, very causally deep might be things that we associate as being conscious because they have a very large inner world, so to speak, because there's a lot of history wrapped up in one physical structure.
Solicited questions from the audience. We'll get to some of those, but one of them is very relevant to the question I want to ask next, which is about the contingency of the relationship between perhaps what past guest Richard Dawkins might call the extended phenotype and the relationship between these self-propagating entities that we call genes, and if that is indeed a prerequisite for life. And Gracie J asks a question that I'll twist around a little bit, but she asks, does intelligent human life have a predetermined path, but it's contingent upon external factors? And she mentions, the dinosaurs, without the asteroid, there'd be no rise of mammals. Without mammals, there'd be no rise of humans. I like to take that even a step further and say that we needed 3 different types of impacts for us to be having this conversation. It needed the dinosaur impact in Chicxulub and 65 million years ago. We needed the late heavy bombardment of the comets to bring the life-giving water that we know, love, and drink. And then, finally, we needed also to have the moon form from this Theia object via this enormous collision of a Mars-sized planetesimal hitting the early proto-Earth. So without those, and without them in just the right order, and in just, if the comets didn't occur until 65 million years ago, we wouldn't be here either. So aren't there so many contingent things that even if life is kind of inevitable, inexorable, that there's just so little probability that the various events will happen all with the right structure that it's basically, gives credence to the thought that maybe it's a miracle. I know we're not supposed to talk about that.
My view on it is everything that life generates is historically contingent. So in some sense, it's the path dependence of living things that has been really difficult to understand from the perspective of traditional physics, because we don't really have this sort of possibility space of bifurcating paths that could be very different with just like one minor event. There's some theories that might accommodate that, but not really at a fundamental deep level. And so, I think that's deeply intrinsic to what life is that life is actually the history wrapped up in the present, and the specific paths matter and they stack on each other. So, we would not be what we are if we didn't have the precise history that we had. As far as how that has an outlook at the future, because I think, part of the question was also, what does that imply for, like agency in some sense, or at least that's how I read it, because there's some future directed part of it. My perception of it is it's actually an active process that living things are actively constructing the possibility space of like what things exist And so I think that things like free will, or the fact that we're actually actively constructing ourselves into the future, is really a very fundamental feature of what life is. And I think, to your point, Brian, actually one of the reasons it looks like it's almost a miracle is because the space of possibilities is so huge. And traditionally, like what has been difficult about life is these very seemingly low probability structures happen with very high probability because they're just so complex. And, if you just asked, based on, the initial conditions of the universe, if I run that system forward in time, what's the likelihood of getting Brian and Sarah talking to each other? It seems like you need very fine-tuned initial conditions in standard physics. Assembly theory basically is a way of formalizing how that information that would specify our conversation gets accrued over time, and why it's stored in the objects that get selected and continue to persist in the environment. So it's a way of saying that miracles are built up over time, basically. So the missing component for miracles is time.
Assembly theory explains a lot, or purports to explain a lot, but there's obviously critics, and it's impossible for me as a physicist to read it and just assume that, as has been said by the dark matter in this book is Lee Cronin. He appears on many pages in writing, and then through his mischievous nature as well. But sort of the unseen force throughout a lot of the book. But he's called it sort of possibly revolutionary to even my field, the most important field, cosmology. How could possibly be the case that assembly theory has relevance long before not only molecules, but before atoms? And a large part of the logarithmic history of space-time that I'm concerned with is before, a lecture week phase transition. So we're talking, trillions of a second.
And it's actually very funny because my book is often marketed under cosmology. So,
Oh, really?
It's like, it's very funny.
As long as that cosmetology, I get that.
I know, right?
Beautiful
I know.
hairstyle,
Yeah, there you go. So I think it's actually very relevant. So actually the first person I heard really making concrete connections in the same way I think assembly theory might make connections between cosmology and life was Lee Smolin, because he has some ideas about whatever theory will solve quantum gravity is also the theory that will solve life, because of this idea that the expanding universe needs some other mechanism. And I think there's some strong indications that something about causation or time might be fundamental to that process to some people. And, that obviously underlies causal set theories of quantum gravity. And so actually the first two people I ever heard saying that, time was kind of fundamental in this way and there might be some connection was Lee Smolin and Lee Cronin. And that was kind of interesting to me because, one's a cosmologist working in this totally different area and another's a chemist working this. It was odd that they both kind of had the same conception. But I think more fundamentally, I've always made the argument that whatever physics solves life. So first off, you have to take, approach the problem the way I approach it. You have to assume that life is a universal phenomena in the universe. And as an astrobiologist, I think that's just something we all implicitly assume, whether we explicitly state it, because we're assuming life has happened on other planets. And so that assumes that there's some underlying mechanism or some universal principle or whatever you want to call it about what it is that we want to call quote unquote life. And if you think that it's not, like specific molecules, like the chemistry of life on different planets, it has to be something much more abstract than that. And obviously that's what gets you into theories of physics. Assembly theory is a way of understanding that really places selection as fundamental. And selection in part is a mechanism of how time moves through the expanding space of possibilities in chemistry with life. So if you look at the assembly space as we define it, what we talk about is this idea that every step in this space is moving into a space that's exponentially growing as far as what possibilities were excluded. So what life is doing is increasing complexity against an exponentially expanding background. And so this starts to have some weird kind of mathematical parallels because it's a causal structure theory. It's about causation in objects, and it's in this expanding space to this idea of causal set theories and quantum gravity. So that's one mathematical connection. Whether there's actually a deep connection between those physics or not, obviously, is subject for debate and actually not even debate. It's subject to like doing the hard work of like trying to validate it's real. So I actually have a new postdoc in my lab who's trained in numerical methods in relativity. And so we're talking about trying to apply assembly theory to explain the expansion of grids and cosmological models, like how you actually perform the computation, as you're modeling expanding universe, as like you have your co-moving distances but you actually have to have a grid underlying them and insert points on the grid. So if you think about the universe as constructing itself, you have to ask questions about where that expansion comes from. And so assembly theory would say it's time. Time is actually just expanding all the time. And so space is getting bigger because space is an emergent property of time. And also when you get to chemistry, the combinatorial space is getting larger because it's an emergent property of time. Whether that part of the theory is true or not, some people will, as you're saying, criticize Lee and I for overreaching. But I think, we can stick to the things that we're experimentally verifying. But the reason for going for these sort of bigger stories is actually motivation about making connections to actually find out what the real theory is, right? So if you look at the history of physics, most of the time people were doing things that seemed very grand initially and then realized that they could actually do it empirically. And there's a lot of evidence that in the history of science, a lot of the most interesting novel ideas and the ones that actually have them, and some of them that have staying power are at the intersections of disciplines. So a lot of what we do is actually trying to see, in particular, this is actually how I work intellectually. I work in I don't know how many fields. And I try to see the same structure about what life is in every single one of those fields because I think it's very deep fundamental physics. And if it's a very deep universal fundamental physics, you should see signatures of it everywhere. And, that's true of motion. That's true of, quantum fields. Like anything that you want to talk about in physics has this property where you can see it in every object once you recognize that physics. Assembly theory is about the physics of selection and causation and how the universe builds structure when it doesn't have structure, like the origin of life. And so that might be related to some fundamental things in cosmology. It might just be a side project that's a tangent just for fun. Either way, I'm really excited about thinking deeply about those ideas. I do actually feel like there's a very deep connection there. And this is a very good explanatory paradigm for what's happening, which is why I work on it.
How do you handle the criticism that, the assembly number plus copy index or, copy number, that those are, fundamentally subject to degeneracies? In other words, there's many, many molecules that, methane is very important. It's a life byproduct, but has very low assembly number and index and, copy. Very high copy numbers, so you might think, oh, this would be really relevant. And the problem of tar and so forth. How do you address the critics that say, look, there's so many things that are bound to have the same, assembly index, copy number, et cetera, that it's an over determined system. There's just simply too much correlation for it to be useful. I
don't understand the structure of that criticism. I don't think I've gotten that one specifically directly. I don't think that's an issue though, because it's actually a trade-off. If you look at so we have an equation, it's called the assembly equation, which is supposed to capture the amount of causation in a configuration of objects. And the idea is if you see very high assembly configurations of matter, then you're observing a living sample. So I think your counter argument is, so the terms in the assembly equation are, you have one term for the number of copies of an object, and you have another term that's an exponential in the assembly index. So you have a linear term with respect to how many of the object you have and an exponential term with respect to the assembly index. The assembly index term, if you have high copy number of high assembly index like that, that thing is growing very large, very fast. And so, this idea that you would have many methane with low assembly, okay. So, but if you want to compare it to the same number of DNA molecules and their assembly, like obviously their assembly value is going to be much higher. And so one of the things we haven't figured out is whether assembly should be an extensive or intensive property. Should it depend on the volume of the system or not? And so some of those things are really aimed at resolving maybe some of these debates about copy number and things like that. So there's still lots of work to do in the theory, but I don't really see that as a valid sort of. It doesn't seem to stick to me that actually counters any of the arguments. It's just
I guess the question is, if it's a valid index, it should be, possible to separate out two different things that have the same metric.
But we can't do that with most variables in physics. I could have things that have the same velocity and I don't know they're different objects, or I could have things that have the same entropy and I don't know I don't know what that means.
Right. But the title of the paper is, explains evolution, explains complexity.
Oh,
I guess the analogy.
No, but okay. So, but you could have things with equivalent amount of evolutionary causation in them that have similar assembly values. I don't see why that's a problem.
Well, I guess, for it to be a valid, I'm just a simple cosmologist, right? So
Yeah. Well,
I'm thinking about it.
but we're all exploring, so that's fine.
Yeah.
Yeah.
No. I mean, and it's not a deep criticism. It's just the question of whether or not, like H index. Let's think about our H indices, right? So we all have them, or RBIs, or in baseball or whatever. You got the Diamondbacks that I hope will lose soon to the Padres, but it doesn't really fully capture the totality of an entity. But it doesn't claim to either. In other words, if you say like so and so's got a high RBI,
see. No, that's fine. Yeah.
Or
so
I'm thinking about it actually as a chef. I used to
Sure.
be a sous chef in a diner in New York where I grew up, and we could take different recipes and follow them, and they'd come out tasting like total garbage, or they could be delicious depending on who made it. So the validity of the recipe or the validity of the metric as applicable to encapsulating something as vast as evolution and complexity. I guess that's again, it's a very friendly criticism.
I totally understand. I think I understand more about the structure of the criticism. And by the way, I'm very happy for the criticism because it makes us think more deeply and
that's
develop
what a real. And I'm sorry, I have to
Yeah.
stop you. Whenever they're so 90% of my audience are young people pursuing degrees in physics or STEM or professors. I've got a huge number of Nobel laureates that watch. Anyway, what Sara just did is, I like to signpost this for my listeners, is the hallmark of a good scientist, is that you are open to criticism, because that strengthens and anneals and makes better your arguments. And so we welcome it. So whenever you hear someone,
It's the most fun part of what we do.
it's absolutely the fun part. And that's the spirit I'm asking the question. So please go ahead.
No, of course I understand that. But when I go into debate mode, it's very intense because I love it. So if I get intense.
I have James Tour. He's waiting to come in a few. No, I'm just kidding.
Excellent. No, I know. Oh my
You did
God.
ask a question. I'll ask you that later, but it's
No, that's fine. It's totally fine. I think I understand a little bit of the criticism. So one thing is whether a measure could capture anything about that kind of, broad regularities. And I think if you look at the history of physics, that's what it's done with every single measurement we've taken. That is part of a broader theory that explains things. So, like the fact that we can reduce much of reality to, like a gravitational constant and measures of mass and acceleration is like really profound. And like, who would think that would capture, a broad range of phenomena? So that's one thing. So one is it's consistent with the history of physics in particular that this is a possible thing to do. And it gets to the nature of whether the universe is comprehensible and why it's comprehensible. So that's a whole separate conversation. But why put explains in the title? And so for me, I think a lot of the criticism of engagement with assembly theory has been like nitpicking various quantitative aspects, like you're saying about like the assembly index or copy number. And, there's been less intellectual engagement on the actual underlying philosophical and conceptual underpinnings of the theory. And to me, that's actually what's more interesting, is what it actually might explain and how it explains it. And I'm very much like a Deutschian in some sense about how I think about theories and their explanatory power. So, I think a whole generation of us has been very influenced by David Deutsch and his writing. But, he talks about, good theories are things with broad explanatory reach, and they're hard to vary. So hard to vary for assembly theory is, we can't vary some of the structure of the theory. Like the assembly index is the assembly index. Like it's not, it can't be another measure of computational complexity or other things like that. Like there are certain things about the theory that are there and they're falsifiable. But, the other feature of a good theory that he points out is that they're very broad in their explanatory power. And what does that mean? Means that they fold in a whole bunch of things that we thought were really different, and they explain them in a similar way. And the depth of the explanation actually allows us to see things that we wouldn't be able to understand or reach for otherwise. And I think assembly theory accomplishes all of those things, because if I'm doing my job as a good theorist and all of our team is doing a job as a good theorist, what we're ultimately trying to do is explain what life is. And what life is, if you ask it from the perspective of theoretical physics, is going to build a theory that doesn't look like what we think life is, because that's what the physics does when you actually ask questions the hard way and you ask nature to tell you what it thinks or what it does rather than what you think it is. There's a lot of things in that paper that are about the explanatory paradigm, not just the formalization of assembly theory, that I think are really important. And that's why, because what we want to say is that selection is actually a fundamental mechanism of how our universe constructs itself when this possibility space is too large. That's an explanation for why some things exist and not others. That goes really a lot deeper than current evolutionary explanations. So Darwin talked about the struggle for existence among existing forms. Assembly theory is about the struggle of what gets to exist. It has a mechanism for that. Like, why do some things start to emerge on these pathways of complexification and not others? We can explain why. We can explain why in terms of the historical contingency. And there's all kinds of other things assembly theory can potentially explain, like the nature of information in life and why it appears abstract, why time seems so relevant to life, why life looks path dependent, how to reconcile life with fundamental laws of physics. I mean, I could go on and on. Like, it is an explanatory theory if it works. It explains a lot. And that's why I'm excited about it, because I'm trained in theoretical physics and I'm trained in deep ideas with broad explanatory power. And that's what I've been after my whole career. And those are the ones that I think have staying power. So what we want to do with the theory is not just test it on one observable. It should be tested against all kinds of experiments in all kinds of different sectors of science. And then you will be able to demonstrate that it's an explanatory framework. Obviously, we're in the early stages of that. So that's sort of, like, there's a lot of things that we're trying to make predictions of that could be tested and see whether the theory is actually accurate or not.
You talk in the book about various hard problems, and
I
love.
I only like them.
Yeah, I love them
hard
too.
ones.
And I love the inversion of the classic questions. Instead of what is life, life is what. I always like to ask. People ask, what is life? I like to ask, how is life? How's it feeling? How's it doing? Really? Okay. But I want to talk about the fundamental, the fundamental question. I asked one of my children today. I told him I was having you on. He's so excited to listen to this podcast, and he's a master of puns and jokes. And
I love that.
I told him, well, be careful what you wish for, sir, because I told him, you're an expert in in DNA and the origin of life and stuff, and he asked me to ask you if you know that that diarrhea is inherited, genetically. Were you aware of that?
No, I wasn't.
Because apparently it runs in your genes. But he did come up with a good question for you, I think, which is how do you know which came first, the chicken or the egg? How can you, as a theorist, or Lee as an experimentalist, determine which comes first, the chicken or the egg? And he has a solution to it. Would you like to hear it?
I would love the solution. I think that's an age-old question. If he's got it, genius kid.
He said, just order a chicken and an egg on Amazon and see which comes first. And then you'll know based on which comes first. Okay. Now, if you use that, you got to attribute it to Brian's son. Anyway,
I will.
In all seriousness, who created the first assembler? And, don't say IKEA.
No one has an answer to that. I wouldn't assume that I do. But
What would you think it is? Speculate. Wow.
I think actually, like, only the current. I'm a presentist right now, and so I don't think. So I think and these are kind of radical views, right? But I think what I'm trying to do is explore. So one thing I do, and this goes back to your point about, like, what is it about science that like we have to do that's hard. And one thing that I do that's quite hard is I don't hold on to any view as like a permanent one I could hold. Every view I have is a working set of constraints about trying to understand the reality in which we live. What the story of life is that fundamentally is written is telling us is that I think the universe is a self-constructing system, and it's constructing itself from moment to moment. And if you look at the past history, you can see some constraints in that space that are about the coexistence of why these structures are coexisting and not others. But in some sense, the way that we're framing it right now is it's kind of random outside of those structures. Like, even if you look at quantum foundations, if you look at quantum mechanics, the experiments are suggesting an uncertainty or inherent randomness until you take measurements, and those measurements build determinate structure out of their correlations. And so this idea that the universe operates as a clockwork might just be an emergent property of the causation between objects and the fact that they scaffold each other and then they allow more existence of things. And so that's sort of the way that I understand it. And so I'm trying to reconcile actually in my own mind this idea of a forward process as I've always been taught, and this idea of assembly theory, which is assembly theory is a weird theory of physics if it pans out. And I actually like this property, but I struggle with it myself intellectually, that it's a theory that takes what exists now, it builds backwards to construct the assembly space of how you got there, and then you use the assembly space to go forward. So there's no initial condition in the theory. The initial condition is always the present moment. And that's very different than standard theories of physics, because they start with an initial condition in dynamical law. And so you run the theory forward in time, and then asking questions about how that process started is more meaningful in those theories, but it doesn't mean the same thing in assembly theory. So I'm thinking about it from multiple sides, and I have lots of ways of regularizing that. But Paul and I had a workshop recently about infinite turtles or ground truth. It was like, what turtle is under what turtle is what under what turtle, and like, is there a bottom turtle? I mean, it's like, this is the age-old question people want to ask. And I think assembly theory offers some really different narratives about it. And I think some of these questions are very culturally and historically specific about how we even ask them. So I think that's also something that we need to keep in mind.
You said nothing is off limits, and I love that about you. You're fearless and courageous intellectually. So I had on guest Dr. Stephen Meyer, who's a philosopher. He's written many, many things, including Darwin's Doubt. And he always makes the case, and he did when he was on the podcast about 3 years ago, that, there's no case of information arising spontaneously. You go into a cave in Egypt and you see some hieroglyphics. Yes, it's supposed theoretically possible, windstorm could generate that. But if you look at all sorts of sets of information, it usually can be traced back to a mind or, some pre-existing intelligence. I guess this dovetails nicely into what you just said. But how do you react to, those that support intelligent design? I mean, should they be shunned? What do you make of this?
I just would like, I'm a scientist. So, I became a scientist because I want to test my ideas against the way the world works. So actually, one of the reasons I became a scientist was when I was at community college, I was taking physics. And I remember the exact lecture I decided I want to become a theoretical physicist. My professor was talking about magnetic monopoles, which are things that we mathematically predicted, and we could go out and test for their existence. And so it was the idea that our minds could come up with abstractions, but we could actually test them objectively against reality through the process of science that really made me want to become a theoretical physicist, because what I want to do is be confident that the abstractions are actually really out there. And so I don't reject intelligent design as a hypothesis or like it, an idea people want to think about offhand. I just don't find it particularly explanatory. It doesn't really help me solve any of the problems I want to solve as a scientist. And I don't see the sort of measurable consequences of it. Like, how would you test that theory? And so it doesn't seem to me to be a good explanation. I don't think it's impossible for people in that community to come up with better ways of building experiments to prove that there had to be a designer. I mean, this is basically what we're trying to do with the origin of life, is build experiments that prove there wasn't a designer. So it's possible to think about the problems from that perspective. And it's possible to quantify the information that goes in from design. Assembly theory is doing that. So we should be able to get to the bottom of that question about whether life is designed or not, and be able to validate that the universe can do it without a designer or it requires it. But I don't feel like that community is really engaging with the question or trying to solve it, because they would rather say it's design and then say it's design. But, if it's design, you should be able to do an experiment to prove it.
Yeah, I mean, I feel like they rely on kind of disproof in the sense that they'll posit how difficult it is to have life arise via purely random processes. They'll point out, one of the listeners has a question for you about, can you identify all the pathways of abiogenesis? In terms
you don't need to with assembly theory. That's one of the great things about it. You do need to do that in standard astrobiology for like false positives and ruling them out, but assembly theory doesn't have that problem.
In terms of, the first living cell, like if you just started that as your building block for life, it could be prokaryotic, eukaryotic, whatever. How is that accounted for within assembly theory?
What's the exact question? I don't understand the last part of it. Sorry.
Can you limit the time frame for the completion of each independent pathway within an abiogenetic framework?
Oh, sure.
Leading up to a cell at the end of its production.
Yeah. So I think one thing that we have to be careful about is like, what concept of time are you talking about? Are you talking about causal time, which is like the partial ordering of events, or are you talking about clock time, which is like the ticking of seconds on a clock? And I think something was just as sort of like a historical philosophical background. I think something we take for granted is that every theory of physics, in some sense, carries with it a new concept of time and refines our concepts of time. And so if you look at like Newtonian mechanics, it invented the idea of clock time as being fundamental to the way the universe operates. And in part, that was because of the technology of the day that enabled Newton to invent gravity in the way that he did, was because we had mechanical clocks, and Galileo was able to take precise measurements, and so was Tycho Brahe. Second law of thermodynamics gives a directionality to time. Einstein talked about simultaneity, and assembly theory is one that is about causation and about partial ordering of events. And so what assembly theory says about time is there is a minimal partial order in some sense, a minimal ordering of things that have to be constructed in order for this thing to exist. And I think that there is a way of relating that to clock time, like what would be the minimal amount of time in order for the universe to produce this particular object. And I actually think this is one of the best windows we have to experimentally validate, in fundamental physics experiments, that assembly theory is the right way of doing things, because for any complex object, there should be a minimal construction time. It should not spontaneously be able to fluctuate into existence. So if you want to ask about an experimental, paradigm to compare what assembly is saying to intelligent design, I think intelligent design would say anything can spontaneously fluctuate into existence in an instant because there's a designer and the designer doesn't require time. And assembly theory would say an object has a time scale associated with it for its existence, and there should always be, for any complex object, a minimal amount of time in order for that object to come into existence and a minimal amount of constraint. That's actually an experimentally tractable question. I've been talking with Lee a lot about how we can do that because he's so brilliant in designing experiments. But bringing it back to this origin of life question, the question about how do we have enough time? One of the things that we see that happens often in life is that evolution happens much faster than standard theories would suggest. And I think assembly theory is very consistent with that because you have a huge collapse of the space of possibilities when things are self-reinforcing structures. And so the evolutionary events that we care about, the ones that led to us, should happen very fast in assembly spaces. And so I don't think, and the relation between assembly time and clock time is a very, complex and rich theoretical question that we're thinking about, but that would be sort of, like another frontier that we need to deal with. And I think one thing for your listeners that's really important, I talk a lot about the history of physics, but this is like super exciting because this is like for me, because it's a new theory and we're getting all these really hard questions, and it's all stuff that we're trying to work on. So I like the questions because they help us focus what we really need to convince ourselves, but also our peers about the physics working. And actually some of the hardest questions I get about assembly all the time are from my students. They're like, because they're working on it, so they really want to believe it, it's going to be the right explanation. And then they're digging in all to the holes and what about this and what about this, and I think about the early days of quantum mechanics. It's nobody knew what was going on or what it was going to be able to do, or any theory. So this is kind of a fun moment because we're trying to figure out all these things, but that would be sort of the way that we're thinking about it from an assembly theoretic perspective, and also why it would be consistent with what we've observed and what we can test.
Hey there. I may not know what life is, but I sure do know what fills my life with joy, and that's seeing you enjoy these deep dives into the most important topics in all of science as much as I do. Even after all these years, I still get a thrill from every new subscriber, like, and comment. So if you're enjoying the show, please do hit subscribe on YouTube. It really helps us with the algorithm that governs my life as a YouTuber. And please follow the podcast on your favorite podcast platform. Give this episode a rating, a review, and a thumbs up. It really does bring a lot of joy to me. Now back to the brilliant Sara Walker.
The question of whether or not you could find evidence or find a justification to either retool assembly theory or maybe, God forbid, it's wrong. And that came up to me as, because at the end of the book, you start talking about, making these lifelike entity. I can't think of a better name for them, but, you're basically making your own life. And you claim that might be the best way to find aliens is to make them yourselves. What set of kind of behaviors or thresholds would you need to do, or trials, as you call them, in terms of creating life in the lab, would be sufficient to give up? I mean, we all have to pull the plug on our experiments at some point. Is that beyond the horizon, not just a tenure or?
Yeah. So I think a hallmark, while we're talking about hallmarks of good scientists, a hallmark of a good scientist is they are willing to abandon their favorite idea. And actually, sometimes because, assembly theory originated with Lee. So in some sense, I've already kind of done that because I was developing some other ideas and I was just so compelled by the structure of the ideas and the resonance between what I was thinking about what he was doing. I was like, I had all these other ideas about information theory, causation, all these other things I had been working on with a variety of different people. But I found the assembly theory framework to me to be personally most convincing, which is why I'm investing my time and resource in it and really working on building the theoretical foundations of the theory with Lee. But so it's not, and I don't agree with some of my earlier papers, actually. Like, I think this is also something, scientists go through, like, not in a bad way. Like, I don't disagree with them. They're not wrong. I just wouldn't think about it that way anymore. So I think there's always sort of an evolutionary progression in how you think about things. So that's one thing underlying the scientific process that I think is really important for young listeners, is like every idea you have is subject to revision and changing your mind about things. So I think there's a couple answers to your question. One is, the holy grail for like this, the kind of like validation I talk about in the book, because it's the easiest and it's also the one I'm most excited about, is validating that we have solved the origin of life in an experiment in the lab. And there's a couple hurdles to that are, on the level of like the theory might not work. And then when do we quit? And then there's also the, like the reality of the situation, that we don't know whether life is an easy mechanism or a hard mechanism. So we don't know how long we'd have to be running such an experiment. So the analogy, from my cosmology background that I make in the book is to the Super Kamiokande experiment, which is looking for proton decay and hasn't observed it yet, but can bound the probability. And I always imagine an origin of life experiment being something like that, because if you think like a cosmologist and you're saying, I want to know the probability of life on any planet in the universe, not just here, the real way that we should be talking about origins of life is to understand the likelihood that chemistry could generate life from geochemistry. Like, how do you generate biochemistry from geochemistry? What are the statistical odds of that if you have a random prebiotic soup engine running for billions of years, right? So the idea in the book that I present is to actually encapsulate that in a large scale automated chemistry experiment and treat the origin of life as a search problem. So the search problem on its own and that idea is in some sense independent of assembly theory, because you could run a search engine without the theory and just try to look at what chemistry you get. Now, the question is, we don't know how to measure life, and that's what assembly theory offers, right, is the measurement of the complexification process and how much evolution has occurred and whether evolution has happened spontaneously in that system without a prior evolutionary architecture, which is the critical question in the origin of life. So I think that experimental paradigm will be useful and provide useful data independent of the theory, but I think it's a really good test of the theory. But the theory itself is also, as I said, we're trying to test it in a variety of different ways. And so I already mentioned this, but I think, any good theory, like if it's as deep, as fundamental theories of physics, needs to be broadly explanatory and to be able to have application in a variety of domains. And so one of the things that my lab is doing and Lee's lab is doing and some of our collaborators are doing is trying to apply assembly theory in new spaces. So some of them are constructing phylogenetic trees in the absence of genomic data. Lee's lab has a beautiful paper that they just submitted. It's not available on the archive yet because they're patenting some of the technology, but where they actually show that they don't need genome sequence information. They can actually just use molecular information and mass spec and assembly theory to create accurate phylogenetic trees, which I think is also really important for origins of life because it means that we can reconstruct phylogeny before the genome. And that's important because right now the last universal common ancestor, which is, the first thing that, structures on our planet that had genomes, is, as far back in time as we can get. It's like the surface of last scattering, but for biology, which I think we've talked about before. So being able, like, if we can make inferences about chemistry that happened before Luca and test hypotheses about that, but also, what we're doing in my lab now is looking at viral evolution, which has been really hard to build trees, and we're applying assembly theory to that. And I think that there are ways that we can talk about the complexification of viruses that people haven't been able to articulate before. At least that's the hope. Obviously, work in progress. And then, other spaces are in material science and thinking about assembly of crystalline structures. So we have a paper that Lee's lab has been working on. I haven't really been involved in, but they've been doing crystal assembly. And I think that's also a phenomenal piece of work because it allows you to talk about the technology of engineering materials. And another application is in drug chemistry and predicting new molecules with drug-like properties, which can be tested. So the theory can work in lots of different places. And some of them we have validation in already, which is, so to your point, like proving a good theory is that it's actually useful. And when it becomes useful and does things other things can't do, then it becomes a part of the structure of science. So I don't think theories die because of one experiment or one failure. They die over time because they don't actually have any utility and nobody can use them to do anything. So ultimately, the proof of assembly theory is going to be, is it a good explanation for life? Does it allow us to do new science we haven't been able to do otherwise? And what kind of things can we do with it? And what kind of new questions can we explore? And that's why I'm excited about it, because I think it's just opening up a new frontier. The other one, actually, sorry, Sorry. I know I'm on because I'm excited. But the other
Yeah,
one I'm
of
really
course.
excited
I
about,
love
which
it.
is not really testable, is predicting, like it is testable in some sense, but it's a longer term horizon, is I always thought it would be great if life detection was a predictive science. So right now in astrobiology, when we want to go look for life on other planets, we're like, let's go look for amino acids or oxygen in a planet of an exoplanet atmosphere, or DNA on Mars. And it's always like, take a molecular structure from Earth and put it on another planet. Let's try to detect it. And assembly theory offers us this way of just saying, let's go look for complex molecules. But because of the structure of the theory and the way that we can iterate through chemical space and talk about evolutionary pathways in molecules, embodied in molecules in the history, embodied in molecules, we actually have a way of taking planetary geochemistry and trying to predict what kind of biochemistry might emerge out of it. And I'm really excited about that because it starts to tell us something about what kinds of life could emerge on planets or what kind of chemistries could emerge on different planets. And I don't know how far that's going to go because that's, like chemical space is so large, it's going to require a lot of artificial intelligence to like actually train algorithms on assembly theory to try to predict these kind of chemistries on these planetary bodies. But that's something I envision as a long-term research question.
Yeah, of course. And speaking of planetary life, and you mentioned Mars, and it gives me a chance to segue into my favorite topic, which is myself. No, which is discussing, the reasons why I'm not an alien optimist. And I brought this up when I was on with Joe Rogan. I'm curious, Sarah, did he have the Mars rock that I gave him, or has
Oh,
he?
I don't know. He had a lot of stuff on his table. So we talked about some fossils and things like that. And I didn't notice in particular a Mars rock.
Okay, yeah. So I
Yeah.
gave him a Mars rock.
He
I'm
has
just
quite a
hoping.
collection, though.
I'm hoping he didn't try to smoke it or something like that. That'd be dangerous. But we talked about, this fictitious scenario where I tell him or I'll tell you, and let's skip Joe Rogan for now. Sarah, I just found out that my friends that use the James Webb Space Telescope have observed a binary planet system where these two planets are in roughly the same orbit. They're in the Goldilocks zone, and one of them is teeming with life. It even has creatures on it that look around and they look at these slabs of glass and plastic and then there's the other one. We haven't had time to slew the web over and look at it. But it's going to cost about $1 billion to target it for a week or 2 weeks or a month, whatever it is. And of course, it means we're not going to be able to look for the other cool things in cosmology that Brian Keating cares about. So tell me, Sarah, would you think, given the existence of life on one of the two planets, call it He3, that the other one, which I'll call SRAM, would have life? I mean, would you expect, based on Bayesian reasoning, that the existence of life on one of the two planets in a Bayesian framework, that one of the two planets in a binary system would imply the other one should also be teeming with life?
I think that's a hard question to answer at this stage because I think you'd actually really have to understand. So I think in principle, yes, I might expect it. I think it requires a good underlying prior model. So again, this is my scientist hat. Like, I don't want to answer you till I think deeply about the problem
Right.
and have like a really like concrete idea about
I mean,
it. But if I
obviously,
were
I'm talking
to
about Earth sharing
yeah.
material with Mars, reverse
Yeah.
panspermia.
Yeah,
So,
but I have thought about this a little bit in terms of like technology, and I think like one of my favorite techno signatures is two planets that have very similar atmospheric composition. And so this idea that like, life on a planet evolves to sufficient technology that the planet itself can reproduce life on another planet, and we might call it geoengineering, but I think that's a very real possibility that at the level of technology, planets nearby will be inhabited, pending life can evolve that far. But my feeling right now is that yes, that is sort of the inevitability of what life is doing. Of course, I'm sitting at a period on a planet where we're starting to launch stuff into space, and we're kind of optimistic about our space future. So, or at least, and I'm an optimist. But I think also from the structure of the theories that we're building and the explanations that is the sort of consequence of what life does. So at that level, yes. At the level of microbes and things like that, I think life is actually, I really think of life as a planetary phenomena. So I don't, this idea of sharing microbes between planets and then starting like, a whole biosphere from a couple microbes, landing on a planet, I think is a very low probability thing. I think it's actually, in some sense, I feel like it's much more likely for the geochemistry to emerge a biochemistry and like ecosystems and things that then, cascade in sort of the structures that they build on a planet. So I have a much more sort of top-down origin of life kind of mechanism in my mind. It's very much like life emerges across all scales on a planet, like from individual molecules to like, planetary cycles. And you see that in modern life. Like, we have molecules that change the atmosphere of the planet. So I think, the idea of it transferring, pre-technology to me is a harder sell. I don't think it's impossible. I don't, and all of this is sort of me just riffing on your question because these are very speculative. And then the question of whether two independent origins could happen is also super interesting. And we don't see that in our own solar system so far, but we also don't know if any of the other planets are inhabited because we don't have a way to test for inhabitants or to test for life on these other worlds. We have, some ideas that we've been trying to look, but we don't really actually understand the phenomena we're looking for. So whether we succeeded or not is not even something that we can say definitively. So that again gets back to the idea of like, what is the likelihood of life emerging on a planet? And, if we find one other planet that has life, maybe that means the probability is higher. So it's likely that another one in that same system could have life. But I think all of these questions, all of them boil down to me to understanding the mechanism of what life is. And then we can talk meaningfully about these questions. But I almost, like for me and the way that I've structured my thinking, I always go back to first principles because I think these questions are so hard unless you have a foundation that you can start from, like the fundamental mechanisms of what life is and then build into asking these questions. And I think, a lot of the stuff you'll see in the literature is people, being very creative and trying to come up with ideas. But it's like, trying to talk about planetary motion before we have gravity. It's like, talking about epicycles and things like this, like they're okay models. They do the job, but they're not really getting at the core question. And the core question for me is like, what is the nature of life in the universe and how do we talk about it? So I tend to focus there. And then when I have that theory, which I have in my mind now with assembly theory, then I reason about everything else from there. And then that allows me to build back into the theory and try to enrich it by like what kind of things we could test or what we could find and what we could predict.
Last week, you posted on X, there's only one example of life on this planet, and we are all temporary instances of it. But we are entirely unlike particles as instances of fields or other current physics because our history propagates through us. So our time to exist as individuals is only now. I want to ask you, pertinent to that beautiful post, if you knew that life didn't originate on Earth, how would that affect you? How would that affect your work? What implications would that have for assembly theory, if any?
I have never taken as a prior that Earth emerged like as a structure of my reasoning. So there is sort of a traditional debate in the original life field about panspermia and like whether life came from somewhere else and arrived on Earth or whether it arrived somewhere, and so, in my field of original life research, the parsimonious assumption is that life emerged on Earth, and that actually makes it more scientifically tractable, which is one of the reasons people adopt it is, like the best argument for saying life arose on Earth is actually we know more about Earth and therefore we can ask the question more concretely because we actually don't know the answers to that question. And for me, I take that actually one step further. I've always, at least since I matured as a scientist, I think I've always thought about the origin of life as an experimental problem in the lab because we don't know the historical record of early Earth. And so I think when you put it at that level, you need to talk about the mechanism. And again, once we have the mechanism, we can talk about was it plausible that it could have happened on early Earth, or can we now ask a concrete question about where it did happen if it couldn't have happened on early Earth. But I'm almost in some ways, I'm not interested in the historical question of how life arose on Earth. I'm not saying I'm not interested in it. It's just for me, like that's a second question after you understand what life is and you understand the actual experimental process of testing that theory and understanding the mechanism of the origin of life. Then you can go and say, what were the environments? How did this happen on early Earth? And then answer the origin of life on early Earth question. And that might open the possibility of speculating about panspermia and things like that. I guess part of what I'm raising is there are a lot of questions in the space about the nature of life and how people think about aliens, origins of life. And a lot of the questions to me have been really unstructured and unrelated to each other. And so most of what I've been trying to do is try to find the question that you can actually answer. And then you can work to the other questions from the one you can answer. And that's also something, like I'm sure you do this, Brian, also when you sit down with your graduate students, they have all these grandiose ideas of all the things that they want to answer in their career. And you're like, okay, well, that one's not getting done in a PhD. Like what question can we answer? And so I guess I'm thinking like in my lifetime, I want to understand something about the nature of what life is and how non-living things transition to living things and how we got to be here, right? Like the question is like, what are we and how did we get here? And so I have tried really hard to turn those really deep philosophical and hard questions into ones that are tractable and we can actually answer. And so I'm really interested in these other questions, but to me, they're second or third order questions you can ask once you understand those more fundamental questions.
I can't resist because you're so good-natured and cheerful and energetic and such a good scientist that I can't resist to ask you both, supportive questions and provocative questions. And this one comes from not a listener, maybe he is, maybe he's not, Johannes Jäger, who wrote in the journal Molecular Evolution, Assembly Theory, What It Is and What Does It Not Do. And eventually cuts around to saying the first major issue is that the paper's entitled Assembly Theory Explains and Quantifies Selection and Evolution, when it does absolutely no such thing. In fact, assembly theory is not specifically about Darwinian evolution by natural selection. And besides, the paper uses that term selection in a very broad sense, so that no biologist would recognize. This leads to unnecessary confusion as evidence from the angry comments, blah, blah, blah. To make things worse, the abstract is a textbook example of how not to write an abstract. It's phrased in vague and hyperbolic terms that are misleading. We'll come back to that later. He goes on with a bunch of other questions. How do you know who this person is? And do you have any reaction to this criticism?
I did read the paper. I don't really actually understand the criticism. It seems to me that some of the ways that people engage with the work are really informed by their own biases about what they think life is. There's some people are like, well, there's no function in assembly theory. Life is clearly about function, or life is about meaning, or you didn't account for this thing that I think is important, therefore your theory is wrong. My reading of that was kind of from that perspective. There were a lot of philosophical arguments and counteractive sort of biases, and I can understand why people would adopt the framework that was proposed or the perspective. But I've thought about those things. Like I've thought a lot about the nature of function and, possibility spaces and all of those kind of things. But I don't find them very constructive when you really want to get down to actually solving problems. So I think that's actually a philosophical discussion, not a scientific one. And it's fine to have those debates. And, it's up to people, it's up to philosophers if they want to, I think an interesting conversation to have about assembly theory, if it proves successful, is how do we want to understand what it says about life? And how does that make us think about the nature of what life is? And there are all kinds of really interesting conversations about the nature of meaning and other things it might touch on, but there are some it won't. And so I think that's fine. But I think to write off a new idea, basically saying it doesn't satisfy your criteria of what you think is important is a little bit silly.
Well, one thing I'd love to get your take on, just because I think you're an excellent explainer, teacher, and I do want to talk about being a professor nowadays and how it's changed in the last 4 years that we've been together on since the Clubhouse days. It seems to me that copy number kind of represents a overall probability above random, which then kind of highlights the question of, who's to say what is random. And we also get into a discussion, you make it in the book, about entropy as sort of representing different states. And you use the classic example of, a coffee with a separate, glass of cream. And then before they're mixed, they're highly ordered, very separated, and then pour them together and they become this jumbled mess of very high entropy and very low enthalpy or ability to do useful work and so forth. But I've always kind of had a bone to pick with that analogy, not with you, but I use it too. But it seems to me that entropy at that level is scale dependent. In other words, if I were to say I totally agree with that. Quarks. Yeah. If we look at the scale of quarks, the coffee mixed together has no difference.
Yeah. No, I totally agree. I've always had a problem with entropy for this reason.
Yeah.
This exact
say
reason.
more about that.
No, I think entropy is label dependent is what you're saying. It matters what scale you observe it and also like what way you decide to observe your system. And, Edwin T. James had like amazing things to say about that mid-century about how the theory of thermodynamics is actually subjective. And, he related it to like, probability theory and Bayesian inference basically. And I think that's a phenomenal amount of like a body of work, basically demonstrating that. So I think we have some indications that and information theory suffers the same issues also, is very label dependent. So I don't take those concepts as fundamental. And so random to me is actually in some sense structureless. And to the level you you can't even identify the structure. It's like immeasurable in some sense, because anything that you can measure starts to have structure. And even if you think about like computational complexity theory is really good at measuring random, but I think the kind of random it measures is already like it produces is already things that are a high copy number, because they're things that can be generated by Turing machines and you can reproduce, some of the statistical features of the structure. So, when we talk about randomness and complexity, I think we're deeply confused about what the universe actually is doing when we say random versus what we talk about mathematically as random. And I don't think that those are the same either. So I think all of these issues are quite deep and hard. And
Yeah,
that's why they're
exactly.
interesting.
Okay, last question from the audience, although it's not really an audience member. It's a former guest on the podcast, James Tour. He says he's read the paper, and of course he and Lee have done, kind of titanic battles, as I'm sure you've witnessed. But he asked me to ask you, some very technical questions that I hope you can address, because I certainly can hardly parse them, pronounce them, and say them to you. But he's talking about the claims of assembly theory that determines and discerns causal history, but how does that translate into a practical relevance? And for those of you who don't know him, he's a believer in intelligent design. He's actually what's called a messianic Jew. I'm a Jew. He's a Jew for Jesus, so it's a little bit different. We have a cordial relationship, but he's very, very into intelligent design, and that's fine. We already talked about that. That's perfectly accepted. He has 700 publications that are refereed and many patents. He talks about how is it relevant for thermodynamically unfavorable couplings of, say, amino acids into proteins?
Yeah, so I've tried to listen to some of Jim's stuff, and I think, I don't know if he goes by Jim or James, actually.
Jim is fine.
James,
Jim's
yeah.
fine.
I think he, in principle, like the motivation behind it to like try to straw man and like, ask questions about the original life community and what they're doing and point criticisms at it is great. But he tends to pick things I think are actually really irrelevant to the problem, and he picks very detailed mechanisms and say, how can this happen? And they're almost irrelevant. Actually, they're totally irrelevant. He's not even asking the right questions. So he's picking apart the wrong questions and saying you can't answer them, therefore you don't solve the original life, without actually engaging with the material, I think, in the way that it's actually presented. And so the question that he's asking about the causal mechanisms in the thermodynamics, there is a sort of challenge that people have often when they're confronted with assembly theory. And I think this is what he's referring to, although I can't really tell from the way that you presented the question exactly what he's getting at. But my inference from what I understand about the way he thinks about the problem, and also what other people have asked, is that, the steps in assembly pathways are not reaction steps. And so, there's a question that people ask. They say, well, this doesn't look like any reaction. Like, these things can't physically exist independently. And it's actually supposed to capture something very different about the nature of causation. It's supposed to capture the amount of minimal recursion in history that necessarily make the object. And in assembly theory, reactions are actually emergent from the assembly space. So reactions don't happen until you have molecules that can interact and make new structure. And they happen under very specified conditions. So even if you take the same two molecules under different conditions, they will react differently. And so the actual reaction that happens, and this is something that Lee's been working on for a while. He has a wonderful set of ideas on the origin of chemical reactions and where they come from. They come from reactivity and process conditions. And this is one of the reasons that he was able to invent the architecture of the computer, and why the computer can operationalize most of chemistry, right? So is because you actually have to understand these parts of chemistry. Like, reactions are not just given to you for free. They are things that happen because you have the right conditions for them to happen. The assembly space is in some sense a deeper structure than that. And, one of the things that, seems a little odd about it also is like these pieces in the assembly space maybe can't exist as independent objects, but they're actually causal features of the theory. And that is also not something that's unfamiliar in theories of chemistry, nor is it unfamiliar in theories of physics. So, for example, if you go into thermodynamics, is being pointed to here, and you want to calculate thermodynamic properties of molecules you don't know, you can do it by understanding thermodynamics of properties you do know. And you actually use fragments of molecules that can't exist thermodynamically independently to actually estimate values and make accurate predictions. So you have a fragment of a molecule that makes an accurate prediction of thermodynamic properties of a whole molecule. So fragments actually do carry information and causation in them in some sense, or some kind of but more importantly for me, like thinking about theories of physics, quarks never exist as, isolatable structures. We have like the theory of confinement, right? So like quarks are always bound structures, yet we understand they exist because we observe their consequences as bound objects. And we also understand that the theory that accounts for quarks as being differentiated objects is very important for what we do in quantum chromodynamics. In assembly theory, the fragments, we actually talk about them as virtual objects. They have causation, just like the physical molecule you observe, but the structure of the actual fragment pathway is critically important for making predictions and actually inference about causal history. And so, for example, where that information is one of the reasons that we can construct phylogenetic trees is because of the structure of the assembly space and taking that as serious. So I think this idea, like it's actually a problem of mapping descriptions and ontologies that are totally different and thinking they're the same. And this is kind of true across a lot of the people that you have cited as having challenges with assembly theory. And this is often what happens in new areas of science. People have a way of thinking about the world that they bring into how they're interacting with any set of ideas. And what we've been doing, because we're such a multidisciplinary team and people with really different training, but we're all thinking very deeply, is we built something that doesn't look like any of these areas. And so if you walk into it kind of blind and not like ready to openly engage with the ideas it's presented, it will look weird and it will look like it has problems and like this thing doesn't work and this thing doesn't work. But the structure of the theory itself, in the self-consistent language that we talk about it, makes a lot of sense. And it requires a bit of an open mind or trying to get rid of your disciplinary dogmas to interact with it. And I think that's actually quite hard for all of us. I mentioned already, I have an issue that I still can't get rid of, like this dynamical systems view in my brain. Even though the problems I work on tell me that's not the right way of thinking.
Old
about
habits
it, 'cause I was
die
trained that way. And I noticed this very early on working on Origins of Life. It was like, you go to a meeting and it's like all the prebiotic chemists think like the issue is one of organic synthesis and you're going to make this molecule. And all the bioinformaticians think they just need to get, a better inference on like what tRNAs were present around LUCA. And, and the physicists would think it's a metabolic, network and energy harnessing. That was the first thing. And the molecular biologist would say, no, we have to get a replicating molecule. So everybody is just bringing in the perspective from their field, and nobody, to become a thing in itself, like people have to just confront the problem head on. And that's what we're trying to do. And it does build different intuition and different ideas about what the nature of the problem is. So that was part of my comment about thinking about the exact reactions biochemistry uses, I think will get you nowhere solving the origin of life. And I kind of agree in that sense. But I think the fact that Jim wants to just stand up and say, therefore, you can't solve the origin of life, is he's stuck on a problem that obviously is not going to solve it. And therefore, he should move to a different problem if he wants to help the community and actually solve it. But I don't think he's interested in solving it. I think he's interested in pointing out problems.
I think it might not help his case or hurt. It might not hurt his case. And Lee says things that are provocative about, origin of life is a scam, all sorts of fun things that Lees want to do, right? But that's science, and that they actually debated.
Well,
which
I
is
think
great.
the other thing that is happening here is, conversations are happening across a lot of levels. And so, as you know, like we're all interacting like socially with social media, and people have their, like their soapboxes they have to be on, and people have to feel like they take stances. And I think some people are well motivated in that and some people aren't. And it's very easy to spot the difference. And from my perspective, there's the deep scientific conversations that we're having and the ideas we're building. And, the 15 or so people in Lee's lab and my lab that are students and postdocs working on these ideas, and our many collaborators that are really brilliant scientists also working on these ideas. So it's not just like Lee and I, there's like a whole team of people. So there's what we're doing there. There's like coming up with the new concepts, taking the time, which it takes, a lot of time to build a new idea and actually do it rigorously. Some of these papers take years to write. And, people are asking us to prove this thing that we're trying to do. And we've been working on it for 2 years and we're not convinced ourselves yet. So we're still working on it. And like, we'll show you when we're ready. And then there's like the public conversation about what the problem is, the cultural discussion, which is, kind of a shifting landscape. And then all of these individual people coming from their deep perspectives. So all these things are colliding, and it's super interesting and exciting, but it's hard to, parse. But I think the important thing is intellectual discussion is being had and new ideas are being thrown out there, and it's hopefully changing the landscape, because this is a field that has been stuck for a really long time. And I personally feel that like solving these problems is really important. And Lee's style of being very provocative is specifically because he's a very impatient person and he likes to just cut through stuff and just go right to the critical debate. And then, but it can be a little, I think he's amazing. And he's one of the most brilliant people, if not the most brilliant I've ever met. But I understand that, people interact with everyone differently. So
let me conclude this wonderful conversation, which will warrant a part two at the latest when the book comes out in paperback next year, but certainly maybe even before then. This is too much fun, but alas, a Friday night dinner calls around the Keating household in a little bit. But I want to summarize with a character who also plays a role in this book, and I think it might be the first book he's ever been mentioned in by name, and that's our good friend Sasha, or Lex Friedman, who is a denizen of the internet that we all know and love. He makes an appearance, and I had the occasion of going on with Lex 2 years ago, and I said, he said, well, the reaction once life is discovered elsewhere in the universe is going to be amazing, and it's going to change the world. And I said, I can't disagree with you more. In fact, we already know what will happen the day after life is discovered, and that's essentially a yawn, a shrug, absolutely nothing. Because as you point out in this wonderful book, Sarah, it happened once in 1996 on the White House lawn with President Bill Clinton. And you go through that whole story. And if you actually look up, as you do in this book, and I encourage everybody to read it, it's such a, and the reaction when I posted on Twitter that you were coming on, or X, and on my YouTube channel, both of which are places people can ask me questions online. But when I posted it, everyone's like, oh, I love this book. It's great. It's so unique, and it is. But you bring up this topic in the book, and sorry to meander and ramble, but this event, and literally, as I know from my experience with Bicep 2, people still come up to me this day and say, oh, you discovered inflation. No, we didn't. We were disproven. We got flummoxed by little grains of dust in the cosmos, right? And that's because the tendency of the media is to promote the discovery on the front page of the New York Times, and then the retraction, if it ever comes, on page B17 of the Saturday edition that nobody reads. So people still, the general public does not know that is not scientifically accepted by the mainstream consensus. In fact, the authors haven't fully retracted it. And there's many examples of this. Phosphine on Venus, you talk about that. We talked about there's sulfur life or cyanide life in the Mono Lake here in California. Anyway, Sarah, my point is, I don't think anything would happen the next day after aliens. What do you think will happen if you and Lee and your wonderful students and postdocs and colleagues create life, alien life, or we discover it through a telescope or a microscope or in some form on visiting Earth? What would happen the day after aliens?
I did talk about this quite a bit in the book, and I also wrote about the fact that I think first contact is not an event, but it's actually an explanatory paradigm. And I had this wonderful conversation with Ted Chiang, which I also mentioned in the book. Who's one of my favorite writers and has written about alien contact. But
Arrival is based on his book.
Arrival is based on his wonderful story, The Story of Your Life, which actually was one of the inspirations for me writing the interlude in second person. So, and I've had really long conversations with Ted about his writing. I mean, he's just brilliant. But
he visited us about 6 years ago here.
Yeah, he's phenomenal. But that's cool. Because you have a wonderful center and stuff there too. So but it really hit me because we were talking about like what would convince Ted that we all us thinking about these things and he said scientific consensus, and I had already been thinking we have first contact all wrong. Like, why do we not believe the UFO stories too? I mean, some people believe them, right? But like culturally, we don't believe them, and it's because we actually don't understand the phenomena that we're talking about. So a contact event is in some sense meaningless because it's a contact with what? Like, what is it that we make contact with? What is alien? My perspective on it is science doesn't work by aha moments in most of the paradigm shifting things. It's, decades of hard work and progress. And so alien contact or solving the origin of life is a many decades long project of actually building an explanation. And the explanation helps us regularize the understanding. And so I also did mention in the book this idea that extraordinary claims require extraordinary evidence. And I don't agree with that mantra.
I don't either. I think it's as beautiful as Carl Sagan was. I don't reach into a drawer that has extraordinary evidence for. I use whatever I have.
What you really want is an extraordinary explanation for ordinary evidence, and that's almost always what we have. Or with the exceptions of the kind of brilliant experiments you were working on that take a whole lot of work to actually get the evidence from, right? So it's not ordinary in the sense it takes amount of work. But you know what I mean? Like I'm thinking about like the early history of physics. It's like a ball rolling down a plane. Like that happens every day. Like who would think that that has anything to do with like the force of attraction between the ball and the earth. Like that's
Bringing out
insane.
all my dolls. We got to get
Yeah,
a doll of
exactly.
you
So,
someday,
so
Jessica.
you know, I think there's a lot of misunderstanding in the discussion about alien contact and origin of life, and also in the criticisms of what we've done so far about the nature of science and how science progresses, and what does it actually mean to build new explanations and what sets of ideas. It's never an isolated thing, and this is why I care about explanations so much, because explanations are anchored in many independent lines of evidence that are all pointing to this underlying structure that tells us something deep about the nature of reality. That's what I'm after. That's what life, I think, is telling us something about our universe that we don't understand yet. And I want that problem to be solved. And so that's first contact to me, is when we figure it out.
And that may be when we discover life, but as no one knows it. And we can tell that to the Star Trekians. Sara, this has been awesome. We love you around here. I can't wait. We've never met in person, but I'm hoping that we will someday. Maybe you'll come out and visit us in a month of July or August sometime when it's sweltering out there and lovely here, or vice versa. Sara Walker, Professor Sara Walker. We have so much more to cover. We'll do a part 2. Thank you for sharing so much of your time. Any final thoughts you want? We'll have your X profile, all your book links, and everything else. Anything else you'd like our audience to know about this wonderful adventure that you're on?
I hope people want to think about the problem, because I think it's really hard. And I think we need more people working on deep ideas, whether, I just want people to be excited about exploring. There's so much we don't know.
Well, Sara, have a wonderful weekend. Thank you for sharing your time with us.
Thanks.
And I'd love to have you back on again soon.
If you watched all the way to the end, I know you'll love my first interview with Sara, my interview with Lee Cronin, and click here for a playlist of other fascinating conversations about the origin of life on Earth and in the cosmos at large. See you next week on Into the Impossible.